Welcome back, guys. Day 17. We're doing naming examples today. So this video is just going to be naming examples of all the different types of compounds. So let's dive in. Number 1. Give the names of the following compounds. First thing we need to do is look at what type of compound is it. What do I mean? Is it ionic? Right? Composed of metal, non-metal, opposite sides of the stairs, like far apart on the table. Is it molecular? Or we have non-metals. So sodium, Na, is a metal, and Cl is a non-metal, so this would be ionic. And if we look at these, they're all ionic. They're going to be ionic. How do we name these? Well, we have to check then, ionic, where are they? So if we remember, group 1, which would be lithium, sodium, potassium, rubidium, cesium, francium. Right? Group 2, beryllium, magnesium, calcium, strontium, barium, radium. Group 1 is always +1. Group 2 is always +2. You have scandium. You have silver, zinc, cadmium, and aluminum. All right, scandium is +3 or 3+, plus for silver, +2 or 2+ for cadmium and zinc, and +3 or 3+ for aluminum. Again, I don't care how you write the +3 or 3+. That doesn't matter to me. So these ones do not need Roman numerals. So what do we have? Well, we have sodium. Sodium is group one metal. So all we do is write sodium chloride. All right, the non-metal changes its ending to "ide," and that's it. So B, lithium fluoride. C is potassium chloride. So what is important to spell? It might be your question. It's always going to be vital to spell IDE correctly. So if you say potassium chlorine, it is wrong. Potassium chloride is correct. If we miss a vowel, we do something silly, not a big deal. It's definitely going to be the endings, prefixes when we get to moleculars. The Roman numerals have to be correct. Right? As long as you can successfully communicate what it is, I'm happy. But the endings really have to be accurate. D, calcium, and oxygen goes to oxide. Magnesium, sulfide. Strontium, iodide. And what is G? What is this? So here, we need to recognize that is a thing. Just like this is a thing, and this is a thing, and this one. What are those things? Those are polyatomic ions. So if we don't know those, this becomes much, much harder. Because what would you say? Sodium nitrogen trioxide, which I've seen before. Not correct. It's sodium. And NO3 is nitrate. And that's all it is. Just like H is sodium hydroxide. Potassium phosphate. And again, on these polyatomic ions, the ending still really matters because phosphate to phosphite, different compound. And last, we got magnesium sulfate. So those are some formulas to names for some ionic compounds that do not need Roman numerals. Next up is the same thing. We got ionic compounds, we have metals that do not need Roman numerals, so there's no Roman numerals, except the difference is we're going from words to formula. This happens to be both more common to do and sometimes more of a struggle. The trick, I find, is to write out the ions and then come up with a formula. What do I mean? Potassium, K. Fluoride, F. Potassium's charge, +1. Fluoride's charge, -1. They're good together, so I get potassium fluoride. I would recommend writing out the ions until you master it. And if you never master it this semester, write out the ions. No harm, no foul. Lithium, Li. Chloride, Cl. Lithium's plus, chloride's minus, so we're good to go, LiCl. Sodium, Na. Charge is positive. Bromide, Br minus. So far, this is all 1 to 1. 1 sodium, 1 bromide. Silver, Ag plus. Oxide, O2 minus. So what do we do here? Well, we cross the charges. The 1 comes down. We do not write the 1. The 2 comes down, and we have to write the 2. So we get Ag2O, silver oxide. Magnesium phosphide. So we got Mg. Magnesium is 2 plus. Phosphide, IDE, P, 3 minus. Cross these charges. The 2 again comes down. The 3 comes down. Can't reduce that. So we get Mg3P2. Calcium, Ca2 plus. Hydroxide, OH minus. Cross my charges. Get CaOH2. And there's a problem there. What's the problem? Well, this looks like I have 1 Ca, 1 O, and 2 H's. Well, H2O would be water. That's not what we have. I actually have 2 hydroxides. So I need to put a parentheses around my polyatomic ion. We put parentheses around units, so we know there's 2 of those units of hydroxide. Not 2 hydrogens. We don't write CaO2H2. Don't change the subscripts. We put parentheses around the units and then put a number to represent how many of those units we have. So again, potassium dichromate. Potassium is K plus dichromate, Cr2O7, 2 minus. Cross the charges, and we get K2, Cr2O7. Do I need parentheses there? Well, no, because there's 2 potassiums. Potassium's an atom, so we do not need to put parentheses around the K. In fact, that might be confusing. Sodium hypochlorite, one of my favorite compounds at home. Na plus, ClO minus. It's a 1 to 1. NaClO. Another fun one, sodium bicarbonate. Na plus, HCO3 minus. We're good, 1 to 1. NaHCO3. So knowing these polyatomic ions, knowing their charges, really makes our lives easier. It's not going to make you richer. It's not going to make you more attractive. None of that stuff. It's going to make you have an easier time in this course, in every chemistry course you take. Magnesium, Mg, charge, group 2 metal, 2 plus. Phosphate, PO4, 3 minus. Cross the charges, and we get Mg3, parentheses, PO4, 2. Ammonium. Ammonium's NH4 plus. Nitrate, NO3 minus. 2 polyatomic ions, they are good together. So I get NH4NO3. So that would look like a molecular compound if we did not know our polyatomic ions. However, we've never named a molecular compound that looks like that with 3 different elements and the ends not together, right? That's weird. That's why knowing these makes your life so much easier. Sodium acetate. Sodium would be Na, acetate C2H3O2 minus, sodium's plus. And so we get NaC2H3O2. Now, if you wrote acetate CH3CO2 minus or CH3COO minus, either one's fine. You can write NaCH3CO2, NaCH3COO. I'm happy either way. The reason we do the ones below the line here is it lets you know what type of how those atoms are bonded. We haven't covered bonding like that yet, so that's okay. Chem 1, typically they write it this way, and that's fine. Any of those 3, they'll work for me. Number 3, back to formulas, to names. The difference here is these are metals that need Roman numerals. So now we are ionic, and we need Roman numerals. And that Roman numerals represents the charge on the metal, not how many there are. That's a very common temptation to put, chromium 3 here. There's 3 chromiums, so chromium 3 phosphate. But that's not what it is, right? My best advice is you look at the polyatomic ion here, right? And the polyatomic ion is -3. So how do we get the metal? Well, we uncross charges. So it looks like we have to have chromium, and then there's the parentheses for the Roman numeral, and then phosphate. What's the charge on chromium? Not how many there are. The charge, well, it looks like it's chromium 4+. Right, so chromium 4 phosphate. And this hopefully comes evident right here because we have nitrate, and nitrate, of course, is -1. So if we look at B and C here, I have copper, the parentheses, nitrate, and I have copper, nitrate. Well, they're different. They're different colors. They have different properties. There has to be a difference. Well, the charge on the metal, again, we care about the charge on the metal because it allows us to help predict behavior. Since nitrate's -1, I have to have copper 1 nitrate for B, and I have 2 nitrates here, so I have to have copper 2 for C. The same holds true for D. I have iron and oxygen. So oxygen, we know oxygen's -2. So for D, I have iron, oxide. What iron do I have? Well, if oxygen is -2, this has to be +2 to even out, right? Because all of my compounds are neutral unless there's a charge on them, right? It's a neutral compound. So this has to be iron 2. There's no way around it. E, I have iron. What do you think that iron is? Iron oxide. Well, the 3 came up, right? Uncross the charges, iron 3, oxide. Magnesium, not magnesium, that's easy mistake. It's not magnesium, is it? It's Mn. So this is Manganese, manganese. Very easy. People put magnesium and then sulfate. Manganese needs a Roman numeral. Magnesium does not. So Mn needs a Roman numeral. Well, what's my Roman numeral? If we recognize that sulfate here is 2-, that means manganese has to be +2. So manganese 2 sulfate. And I don't care if we write the Roman numerals like this or like this. So the green or the pink, I'm happy either way. G. G is also manganese. What manganese oxide is it? Well, the 3 came up, the 2, right? Uncrossed charges because oxygen is, of course, -2. So that means we have manganese 3. H. Tin chloride. What tin? Well, chlorine, of course, is -1. So for H, it looks like I have tin, and then there's a 2 chloride. Versus I would be 10, 4 chloride. J here, we have PbO. What's Pb? Well, that Pb is lead. And oxide. What lead do we have? Good question. -2 for oxygen. So that means we have to have a +2 for J. It has to be lead 2 oxide to be neutral. For K, we have lead and oxygen. So lead oxide. What lead? Well, there's 2 times -2 is -4. So there's -4 overall here. So that means I have to have a +4. How does that work? Because it was Pb2O4 and it was reduced to PbO2. Remember, we can reduce ionic compounds. So when we actually crossed the charges, it was Pb2O4. But we want to reduce it again. Why do we reduce ionic compounds? Because they're ratios of cations to anions, right? They're put into a repeating pattern in a lattice. They're not a fixed, small, discrete unit like a molecule. Last but not least, we have tungsten. And carbon goes to carbide. Charge on carbon. Well, carbon be a nonmetal here, so it's -4, right? Negative. Second one's always negative. Remember, it's always going to be positive ion. Oh, what happened there? Positive, negative. So tungsten's got to be +4. Tungsten 4 carbon. There we go. So there are the Roman numerals from the compound. Make it writing out in words. Now, number 4, we'll go the other way. I would, again, chromium 3, Cr3 plus, chloride, Cl minus. What's my formula? CrCl3. Okay, I would highly encourage you, nickel 2 bromide. All right, Ni2 plus, Br minus. What do we get? NiBr2. So this extra step, I don't know why sometimes this extra step that I'm doing in pink here is so difficult for some of us to do. When I was in your shoes, write extra? No way. Just write the extra and get it done, and you'll be accurate. It's much better to write an extra step and be right than try to be, stubborn and get it wrong. Vanadium 5 sulfate. So I get V5 plus, SO4 2 minus. What happens if we cross the charges? V2 parentheses SO4 5. That's it. Lead 4 carbonate. So we get Pb 4 plus, CO3 2 minus. Cross Pb 2 CO 3 4. We can reduce these, can't we, to Pb CO3 2. Now, technically speaking, this one, Pb2 CO3 4, is not wrong. It's the correct mole ratio. It's the correct ratio. We still want to do the Pb parentheses CO3 2. It's much easier, much better for us. right? Because it's smaller, more mass. Not that it's going to be wrong. It's just nicer. We want to do most reduced as possible. Copper 2 sulfate, Cu 2 plus, SO4 2 minus. Hey, they're good together. Plus 2 minus 2, CuSO4. Palladium, PD2 plus, nitrite, NO2 minus. So we get, looks like it's going to be PD, parentheses, NO2, 2. Platinum 2 nitride. PT 2 plus, nitride, IDE is probably an element, N3 minus. So we get PT 3 N2. And titanium 4 oxide, which most of the time you'll see as titanium dioxide for whatever reason. We haven't learned that reason. Ti 4 plus, O 2 minus. We can make this Ti2O4, which reduces to TiO2. And so is that all? That's all of them, right? Nope. Yep, that's all of them. So there's going from the name to the formula. And that's all it is. And we'll have to do that a lot this semester. 5. Now, it even tells us we're now doing molecular compounds. Oh, didn't change color on me. Molecular compounds. So this would be nonmetals, which means we use prefixes. Except for like A. What's A? Water. Whoa. Water. B. Now, if you write dihydrogen monosulfide, I will mark that correct. However, you'll see it as hydrogen sulfide because we don't, if you remember, we do not always denote the number of hydrogens. C. Nitrogen dioxide, 2 oxygens. 4. Tetra phosphorus. 6 would be hexa sulfide. PCl3, phosphorus trichloride. F, nitrogen trifluoride. G is carbon monoxide. And I dropped an O there. If you don't drop the O, I'm not going to kill you. Monoxide would be fine. It's carbon monoxide, but if you write down carbon monoxide, I'm okay with it because I understood what you're saying. Carbon dioxide. 6, hexa phosphorus deca oxide. Now, this A, I'll even write it in a different color for us. This A is dropped. If you don't drop it, I'm okay with it. Last but not least, we have hepta, nitrogen, nona, bromide. So that's just prefixes. A lot of times students find this clearer than the ionic ones because it tells us right there. The prefixes tell us how many. So for 6A, I gave you the dihydrogen there for you. Normally that di would be gone. It would just be hydrogen sulfide, but I gave you dihydrogen because, well, we did. So we got formulas, dihydrogen, so H2S, silicon, Si, tetrahydride, H4, oxygen, O, difluoride, F2, hexasulfur, it should just say hexasulfur, I don't know why it says that. So that would be S6O9 and 4Cl5, C3S7, and CS. There you go. So there's the molecular compounds. Number 7, acids. So let's recap our acids now. We have sulfuric acid. So what is sulfuric acid? No hydro, right? So the ones with hydro do not have oxygen, right? So C, E, F, G, they all have no oxygen. A, B, C, D, no hydro, they do have oxygen. So they come from polyatomic ions. It went from 8, right? Sulfuric, well, it came from 8, so that's an 8. What one's that? Sulfate, SO4. Sulfate's 2 minus, so I need to throw in 2 H pluses to make it balanced. So H2SO4. Nitric comes from nitrate, NO3 minus, 1 minus, it's HNO3. And technically speaking, those we don't write those, right? We don't write those charges. Perchloric comes from perchlorate, which perchlorate is ClO4 minus 1. So since it's minus 1, we get 1 H. Chloric is going to be HClO3, right? Chlorate is ClO3 minus. Hydrochloric. Well, now we have no oxygen, so that would just be hydrogen chloride. HCl. Hydrobromic, hydrogen bromide. Hydroiodic, hydrogen iodide. Acetic, no hydro, comes from a polyatomic ion. 8, acetate, C2H3O2 minus 1. So that means there's 1 H plus. So that's the names, 2 formulas for acids. And just again, it goes back to the naming system with the words. Number 8, a little recap. Let's just do a little recap here. Protons, neutrons, electrons, charge. What's our charge here? Charge would be plus 3. So how many protons does this have? Well, right there's our protons, 92 protons. Neutrons, we're going to subtract those neutrons, right? 235 is the mass number. So 235 is the mass number. That would be the protons. Oh, I haven't read already. That would be the neutrons and protons. So you would take the 235 minus the 92, and you would get 143 neutrons. Electrons. I have 3 less electrons than protons. That would be 89 electrons. So that's the protons, neutrons, and electrons of uranium-3+. That weighs 235. Iron. 26 protons. How many neutrons? Looks like if I take 56 minus 26, 30 neutrons. 3+. So that means I have 23 electrons. Now, or either way you want to do it. Xenon, 54 protons. How many neutrons? Looks like it's 77 if we subtract 131 from 54. Electrons, well, no charge, so 54. Okay, now I have to look at my periodic table. Who has 80 protons? Well, that would be mercury, Hg. I'm going to write 2 of them down. I'll tell you why in a second. 80 protons. plus 2 charge, which means we know that there is 78 electrons. So, what's the neutrons? Well, it depends. Do I put 200 as my mass or 201? Because the mass is 200.59. I don't care what you pick. I really don't. But if it's 200, right, that's 120 neutrons. If it's 201, it's 121 neutrons. So what you put down for the mass determines what you put down for the neutrons. That's kind of important, right? In fact, that's extremely important. Moving on to the next one. I have 117 neutrons, 76 electrons, and I have plus 2 charge. So that means I have 78 protons. Well, who has 78 protons? 78 looks like it is platinum. It's 2 plus. Now we need to get the mass number of platinum. I have to take the protons and the neutrons. I have to add them. In this case, it happens to be 195, which matches the periodic table, but it doesn't have to be that, so we always have to add. Next one, 74 protons is W, and it's 6 plus. Well, what does W going to weigh? I have 183.85. If I throw in 184 down, we can take 184 and we can subtract the 74, and we can figure out that there's 110 neutrons. Electrons, 6 plus, which means if I have 74 positives, I have 6 more positives than negatives. So that would mean I would have 68 electrons. Last one. Now, the last one is not as straightforward. We have 8 neutrons plus a minus 2 charge. Well, this minus 2 charge tells me we are in group 16. Right? Because the anions are pretty much fixed. So group 16. Which of those, chances are, will have 8 neutrons? Well, if I look, oxygen could have 8 neutrons, right? 16, 8, that works. Sulfur, 32 and 16, well, nope, too many. And they keep getting more and more. So this is probably oxygen. 8, 16, 2 minus. So, of course, it has 8 protons and 10 electrons. And that, ladies and gentlemen, is day 17. Hope you enjoyed it. Take care.